Hi everyone, in today's video we will talk about the relationship between solutes and solvents, better known as solute-solvent interaction. So this slide looks nasty. It looks like there's a whole lot going on here, but it turns out we know much of what this slide says. So over here on the left-hand side we have these numbers, 0.0 to 0.3. This is the difference in electronegativities between bonded atoms. Same thing with these numbers, and if you remember back to our covalent bonding unit, we said that if different atoms have a really big discrepancy in how much they like electrons, that dictates what sort of bond forms between them. So if there's a really big difference over here on the right, that's going to form an ionic bond because the difference is so great that they're straight up going to transfer electrons. That gives rise to what we see here, which is these areas of positive and negative charge. And if we throw that into a solvent like water, let me just draw water here. Water has areas of partially positive, so that would be the hydrogens, and partially negative charges. These areas of partially positive and partially negative charges are able to kind of balance out these negative and positive charges that you see here in the ionic salt crystal. That means that these things are able to be dissolved. So because both of those are polar, in fact ionic is so polar it's some other category called ionic, these are going to be soluble in one another. So basically we can dissolve the ionic compound in water. If we have something that's a little bit different, down here in the middle we called these polar. There is a difference in electronegativity. It's not great enough to have full-blown positive and negative charges. We're still sharing electrons here, but we're sharing them unequally. Then we're going to have a situation where we can still dissolve in polar compounds because we have those partially positive and partially negative charges as long as we don't have complete symmetry in the molecule. Because if we have complete symmetry in the molecule, that takes us over here. And if we have complete symmetry, then the molecule itself is nonpolar. We don't see any separation of partially positive and partially negative charges. And that's the same as this category up here, nonpolar. So if you have either a nonpolar bond or you have a nonpolar molecule because you have symmetry, then you're going to have something that looks like there's no separation of charge, which means you're completely nonpolar, which means you're going to be soluble in nonpolar solvents. So this is kind of a review of what we've done in covalent bonding, but the big take-home message is that at the end of the day, things that have similar polarities dissolve in one another. So for instance, lithium chloride is LiCl. This is an ionic compound. It would have full-blown positive and negative charges, so lithium would be positive, chlorine would be negative. This is soluble in water. Water, remember, is H2O, and it has some partially positive on the hydrogen and partially negative on the oxygen. But we're told that gasoline is not. And gasoline is mostly octane, so gasoline is mostly C8H18, which is a nonpolar molecule. So it stands to reason that gasoline would not be able to dissolve in water because this is nonpolar, whereas water over here is polar. The converse is true down here. Gasoline does dissolve well in benzene, which is C6H6, because C6H6 is also nonpolar, but lithium chloride does not. Why is that? Well, lithium chloride is polar. So again, all of this is to say that like dissolves like. So like dissolves like means the following. It means that polar solvents, if I talk about the solvents over here on the left, so these will be my solvents. Polar solvents are able to dissolve polar solutes, so that does work, and nonpolar solvents are able to dissolve nonpolar solutes. But if you try to mix those up, right, if we try to take a polar solvent and dissolve a nonpolar solute, that does not work. And if we try to take a nonpolar solvent and dissolve a polar solute, that does not work. So you can't cross this thing. Like dissolves like means polar dissolves polar, nonpolar dissolves nonpolar. The reason that that occurs is all based on these partial positive and partially negative charges. And it turns out this works in a process called hydration. and that is whenever we are dissolving with water. So oftentimes we can actually make these things called hydrated ionic compounds, which you actually know about. If we go back to our ionic bonding unit, those are the ones that look like this. They're the ones that look like, let's say, CuSO4 .5H2O. So those things are carrying water in them. There's a little bit of water that's stuck in all of these ionic crystals. So what actually happens? Let's pretend that this nice big black box here is a molecule of sodium chloride, and we have some water molecules in the vicinity. So what are those molecules going to do? Well, gradually, because they're liquids, they're in motion, they're going to collide with this black NaCl molecule. And they're going to keep doing that. And much like a hammer and a chisel, eventually they're going to break off, let's say this section of the NaCl, that's going to break off and come over here. And gradually that's going to happen to this entire black box until it's been converted into little, smaller boxes of NaCl, and then water molecules are going to hit those, and it's going to break off even more small pieces. And gradually this thing is completely going to be broken down, and it's going to end up where we have just sodium ions and chlorine ions dissolved in that liquid, and it's all because of the collisions between this water and that salt molecule. So you might be able to predict what comes next. Obviously, if we increase the temperature of this situation, if we increase the speed of these collisions, then the solvation process happens a little bit easier. We've already talked about some things like hydrates. So why is that? Why is it that they have these specific ratios? Well, it turns out that within this crystal lattice of the CuSO4, there are some really convenient spots for water to be kind of housed, and they trap these water crystals, and they trap them in very specific ratios. So for instance, this copper 2 sulfate pentahydrate traps exactly 5 water molecules within this crystal because there are kind of 5 logical places for those water molecules to be housed. So let's talk a little bit more about nonpolar solvents. If we have nonpolar solvents, why is it that they can't dissolve these ionic crystals that have full-blown positive and negative charges? Well, basically, the forces that are holding these things together, these solvent molecules together, are really weak. Those London dispersion forces are way weaker than ionic or hydrogen bonding. And so instead of those collisions ripping apart the solute molecule, they rip apart the solvent molecule. So if you have a collision with a small car and a brick wall, oftentimes the brick wall wins and it doesn't look good for the car. So same thing here, we're trying to collide this little small thing off of a big strong brick wall and it just breaks apart. It doesn't work that well. So what does that give rise to experimentally? Well, we could have a situation up here on the top where we put together a polar solvent and a polar solute, and you'll see that they make this homogeneous mixture. It's all dissolved nicely together. What if we take, though, a nonpolar solvent and we try to collide it with this really polar solute? You'll notice these toluene molecules coming in. They try to break this thing apart, but it doesn't happen because these toluene molecules just separate from one another because their attractive forces, those London dispersion forces, are not that strong. And finally, what if we have, instead of a solid solute, what if we have 2 liquids coming together? Well, if we have a nonpolar liquid like this toluene coming together with a polar liquid like this water, they're not going to be able to mix with one another because the hydrogen bonding of the water is too strong. And so you see this layer that forms that is the separation layer between toluene and water, a nonpolar and a polar solvent. And this looks a lot like oil on water. So nonpolar and polar just really don't mix well together. So we can see this with oil and water, and a really good example of oil and water is whenever you have some nice salad dressing. So if you go down the aisle of the salad dressing in the grocery store, you'll notice that there's a lot of separation going on between liquids and often some solid particles as well. And those liquids that are separating are typically water and oil. And if you shake it, you can shake the bottle enough to get that salad dressing onto your actual salad. But then if you let it sit for a couple minutes, that separation takes over. And again, we have the different layers forming. That's because we're separating out polar from nonpolar. So we have a word for that. We call that immiscible. Things that are immiscible do not mix. It looks like mixable, but it's miscible. So things that are immiscible, notice the IM there, immiscible do not mix. Whereas things that are miscible in one another, two liquids, we call those, they are able to mix, we call those miscible. So this is really specific for liquid solutes and solvents. For instance, we would say between toluene and water, we saw earlier that those do not mix. We would call that immiscible because they're not mixing together. Whereas ethanol and water, these two are both polar. They are able to mix together into one homogeneous solution. We call that miscible. They are able to mix. They can dissolve in one another. They are soluble in one another. So how does pressure play a role into all of this? And to think about pressure, we need to go back and think about gases. So when we talked about gas laws, we know that an increase in pressure can result from various things, right? We can lower the volume, we can increase the temperature, we can increase the number of moles of gas molecules in our container. All of those things are going to increase the pressure, and it turns out that pressure does have an effect, but it only has an effect on gases. So if you increase the pressure, you increase the solubility of gases. Gradually, you reach a point called equilibrium, right? So whenever you increase pressure, you keep having more and more of this gas get dissolved into this solvent, more and more gets dissolved until eventually you form a solution. But if you try to dissolve too much gas, some of that gas comes back out of solution, and then you get more gas over here, and then it reforms into solution. So that we've talked about as this process called equilibrium. And eventually you reach a point where the number of gas molecules being dissolved equals the number of gas molecules coming out of solution, and you reach this happy balance called equilibrium. So what happens if we increase the pressure of the gas? And again, we have different ways of doing that. We can either increase temperature, we can decrease volume, we can increase amount of gas. What's going to happen when we do that is we are going to increase the number of the collisions with the gas particles and the surface of the liquid, which means more and more of those gas particles are going to be able to enter the liquid. And so we refer to that as Henry's law. And I'll give you a moment to jot down Henry's law here in a second. But Henry's law conceptually basically looks like this. Henry's law dictates that as we increase the pressure, in this case, notice what we've done is we've made the pressure go up by a decrease in volume. So Boyle's law tells us that that's an inverse relationship. We've increased pressure by decreasing volume. There are more collisions between these gas molecules and the surface of the liquid, so more and more can be dissolved in the liquid. And that is a result of Henry's law, which states that if you increase the partial pressure, then the pressure and the amount of the gas molecules going into the solvent increases. So basically, if you have the pressure goes up, the solubility of those gases in the liquid will also increase. Now, whenever you undo that, a really good example of this is popping the tab on a can of Coke. You have a process called effervescence, and this is the very rapid escape of gas molecules because they're under high pressure, but if you relieve that pressure, all of a sudden the solubility of the gas in that liquid goes way down and a bunch of those gas molecules escape, and then you have this process called effervescence, which you know as the little fizz that happens. There are still some gas molecules dissolved, right? That soda is still carbonated, but there's a rapid escape because we've rapidly decreased the pressure. So how does temperature increase that or decrease? Well, if we increase the temperature of solutions, typically we increase the solubility of solids and liquids. Why is that? Because as we increase the temperature, we increase the speed of those collisions, so those things are able to be dissolved more easily. However, something that's really strange is that if we increase temperature for gases, the solubility goes down. So let's write all of this out. If we have solids and liquids, if we increase temperature, the solubility is going to also go up. But for gases, if we increase temperature, the solubility is going to go down. So what the heck is going on there? And if you think about the spectrum from solid to liquid to gas, right, as we go from solid to liquid to gas, the way you do that is you increase temperature. So if temperature is increasing to go from left to right here, then the more temperature, the closer you get to gas, which means if we increase the temperature of a gas, it looks less and less like a liquid, right? It's getting further and further to the right here. It's getting more and more gas-like, which means it's getting harder for us to dissolve more in liquid because they don't really mix well together. So it turns out that if you want to increase the solubility of a gas only, you actually decrease its temperature. So let's pause the video if you'd like. We'll get a little bit of practice here and then you can see how you did. So let's imagine that you've taken a little bit of oil and you've gotten it onto your clothing. Maybe you're working on your car. What would you want to do to get that oil out? Should we use water or toluene? Well, in order to think about this problem, we need to know that oil typically is nonpolar. Water is polar. And toluene we discussed a little bit earlier in the video. Toluene is also nonpolar, so because like dissolves like, toluene is going to be a better example, or a better choice in this situation because toluene is able to remove that oil. We'll probably want to use some PPE because toluene is not necessarily the nicest thing for our skin and not necessarily all that healthy for us. We're told that commercial fizz savers, what they do is they pump helium under pressure into a pop bottle. So let's draw ourselves the top of our pop bottle. Here is, here is the top of our bottle. Voila. It's got a cap on it. Voila. We've got the top of our Coke or whatever have you right here. And so this fizz saver, what's it going to do? Well, it's going to pump in some pressurized helium. So helium is going to get punched in here, and we're going to get more and more and more of it. Will this keep CO2 in the bottle? Yes, it will. Why is that? Because as we increase the pressure up here, remember we increase the collisions of gas molecules with the gas molecules dissolved in there. So all of the CO2 that is dissolved down here in the soda, it might want to come out, but as there's increased pressure coming down, remember Dalton's law of partial pressure is that the total pressure is equal to the partial pressure of the gases, so in this case the partial pressure of helium plus the partial pressure of CO2. As we increase the partial pressure of helium, we increase the total as well as the CO2 stays constant, and so that means that we can hold more and more gas, in this case CO2, in our soda. The final question I know you don't have on your note guide, but let's discuss quickly. It turns out that sodium nitrate and sodium nitrate are used as preservatives in meat, and that's important so we don't get a lot of bacteria growing on them, but those aren't necessarily the most healthy things for us. So how might we be able to remove those? Well, it turns out that if we boil meat instead of grilling it, if we boil it, remember whenever we boil meat, we are boiling it in water, H2O, and especially at high temperatures, so if T increases, you increase the solubility of these ionic compounds. So sodium nitrate are Na plus a polyatomic ion. So you have NaNO2 and NaNO3, and those things dissolve well in water, especially water at high temperatures. So you are going to dissolve out those ionic compounds and they'll remain in solution, and you'll be able to take your meat out and you'll be able to eat it and it'll be delicious and maybe a little bit more healthy for you.